Science Help Now here. Topic 6, Work, Energy, and Power. Section 6.4 is an introduction to different types of energy. How is energy defined in physics? In its simplest definition, energy is the ability to do work. Well, if work is a measure of how a force affects the displacement of an object, in other words, how a force helps an object to move or decreases the movement of an object, then you will need energy to displace the object, or to get it to move, and you will also need energy if you need to decrease that displacement. For example, if you have a box on a flat surface and there is an applied force to the right, you need energy to generate that applied force to the right, which is causing the box to move to the right. And energy is also dissipated by the friction force, which is retarding or decreasing the ability of that box to move to the right. Keep in mind again, those two works, the work being done to move the force to the right and the work being done by the friction force to retard that motion, both involve energy. Energy can be transferred from an object to its surroundings and vice versa. Now, there are two ways in which energy can be transferred. The first is by work, by doing work on the object. This is a mechanical transfer. In other words, the object experiences a push or a pull. There's a force on the object. Now, an example of this would be you take a box and you start pushing the box and making it go faster. You have just transferred energy from your body, right, the chemical energy from the food that you eat, getting converted to mechanical energy in your muscles, and then finally to the mechanical energy of the object, where the object is now moving faster and therefore has more moving energy, which we call kinetic energy. So we've transferred energy from our bodies to the box. Now the box is moving faster, it has more energy. The other way to transfer energy is by heat. This is a non-mechanical transfer of energy. When there is a temperature difference between the object and its surroundings, you probably know from other classes, maybe from earth science class, that the heat energy will flow from the hotter object to the colder object. So here we have a quick overview of the different types of energy and a little bit about how to classify them. Energy can be classified as being kinetic energy, and that would be the energy of a moving object, or potential energy. Potential energy is energy that is stored inside the object. Now, these objects that have either kinetic energy or potential energy could be as small as, for example, an electron, or as large as an entire galaxy. Now, kinetic energy, the energy of an object that is moving. You can have linear kinetic energy. The object is moving in a straight line. You can have rotational kinetic energy. For example, a wind turbine, right, spinning around is going to have rotational kinetic energy. You can have thermal energy, otherwise known as heat, the energy of vibrating molecules. The faster they vibrate, the higher the temperature of those molecules. Right now, in this video, we will be talking about linear kinetic energy. We won't be talking about rotational or thermal in this video. Now, for stored energy, gravitational potential energy is the energy possessed by an object that has some height above another object that is attracting it. So, for example, an object on the surface of the Earth, right, you could say that it has zero gravitational potential energy because you're setting the surface of the Earth as zero. As soon as you raise that object up to a height above the surface of the Earth, you can start talking about how much gravitational potential energy is stored in the object. Again, gravitational potential energy is based on the height of the object. Elastic potential energy is the energy stored in a spring. Some types of springs get compressed and they store energy, so they're going to spring outwards. Some types of springs are stretched, and what they do is they spring back inwards. Right? We will be talking about elastic potential energy also. The last kind of stored energy would be chemical or nuclear energy. Chemical energy is stored in the bonds between atoms. Nuclear energy is stored in the nucleus of an atom. So the types of energy that we'll be looking at in more detail in this video are linear kinetic energy, which is based upon the speed of the object; gravitational potential energy, which is based upon the height of the object; and elastic potential energy, which is based upon how much an elastic object, such as a spring or a rubber band, is compressed or how much it is stretched. Kinetic energy is the energy that an object has based upon its mass and its speed. Here's the equation to calculate the kinetic energy of an object. Kinetic energy is equal to 1/2 the mass of the object times its speed squared. Now, in examples 1 and 2, we're going to calculate the kinetic energy possessed by a little girl who is running, and then an electron that is moving at a certain speed. Let's do those calculations now. So, any object that is moving possesses kinetic energy. Let's calculate the kinetic energy of a 30-kilogram child running with a speed of 2 meters per second. So, the equation for kinetic energy, Ke equals 1/2 mv squared. All right, so 1/2 the mass of the child, the mass of the object, is 30 kilograms. All right, and the velocity is 2 meters per second. We need to square that. All right, so half of 30, right, is 15. 2 squared is 4. 15 times 4 would be 60. Now, the unit for kinetic energy, for all energy for that matter, is kilogram. Now, this is meter per second, but it gets squared. So it's going to be meters squared on top and seconds squared on the bottom. So you're going to get meters squared per second squared. And a kilogram meters squared per second squared is a joule. All right, just like the unit for work. Yes, the unit for work and the unit for all types of energies is the same unit, the joule, or the kilogram meter squared per second squared. All right, practice saying that. All right, kilogram meter squared per. All right, when you see a line like that, a division sign, you say per. Kilogram meter squared per second squared is that unit. But it's a lot easier if we just write 60 joules. All right, so yes, this child that is running possesses 60 joules of kinetic energy. Now we have something much smaller. Let's calculate the kinetic energy of an electron, and the electron is traveling at 3.00 times 10 to the 4th meters per second. Now, you can look up the mass of an electron on the internet or on any physics reference table. All right, so here we go. Kinetic energy is 1/2 mv squared. So, 1/2. Now, the mass of an electron, again, look it up, 9.11 times 10 to the negative 31 kilograms. Very, very, very small. And the speed, 3 times 10 to the 4th meters per second, and that gets squared. All right, so let's figure that out. All right, on a calculator. Okay, we've got 4.0995 times 10 to the negative 22 joules. All right, so let's round that, right, to 4.10. All right, 4.10 times 10 to the negative 22 joules. A very, very small number. All right? So again, the kinetic energy of an object is based upon the object's mass and the object's speed. Now let's calculate a change in kinetic energy. We have a 5,000 kilogram truck that increases its speed from rest to 4 meters per second, and then from the 4 meters per second to 8 meters per second. Calculate the change in kinetic energy during both intervals. Now, a change is generally represented by a triangle, right? Delta KE, right? A change in kinetic energy. And a change generally means you take the final energy and subtract the initial from it. Right? If you were looking for a change in temperature, it would be T final minus T initial. If you're looking for a change in kinetic energy final minus kinetic energy initial. This is the way it's generally done in science. Right? Now, the final would be 1/2 mv final squared. And the initial would be 1/2 mv initial squared. Now, the mass of the truck doesn't change. So we don't need m final and m initial. The mass is the same in both circumstances. But the speed, there's a different initial speed from the final speed. Now, of course, for the first interval, the truck starts from rest. So the initial velocity is 0. This entire portion is going to drop out here. So anytime an object starts from rest, the change in kinetic energy is simply the final kinetic energy. All right, so let's calculate that first. Change in kinetic energy, starting from rest, where V is 0. Remember, if V is 0, then 0 times all this other stuff over here is all still 0. Multiplying by 0, this whole portion over here has to drop out. Okay, so 1/2, the mass of the truck is 5,000 kilograms. V final is 4 meters per second for the first interval. We're going to square that. All right? So what we've got here is 4 squared, which is 16. Half of 5,000 is 2,500. So we'll just do 2,500 times 16 to get 40,000 joules. All right, 40,000 joules is the change in kinetic energy when the truck goes from rest to a final velocity of 4 meters per second. Okay, now, let's erase this and do the second interval. The second interval, we start at 4 meters per second and go to 8 meters per second. Notice that the velocity of the truck doubled. All right, so here we go. I'm going to leave that same equation up top there, all right, because we're trying to calculate the change in kinetic energy. Here we go. kinetic energy final, 1/2 mv final squared, minus kinetic energy initial, 1/2 mv initial squared. All right, now in this case there's no zeros, nothing's going to drop out. Now you could factor out the 1/2 m. You could do that. Let's do that. Let's do it that way next. All right, this time I'm going to plug everything in here and plug everything in over there. All right, we'll try factoring out later. It'll come out the same. All right, so 1/2 m is 5,000 kilograms. V final, okay. V final is 8. We're going from 4, an initial of 4, to a final of 8 meters per second. All right, so V final is 8 meters per second. Make sure you square that. Minus 1/2, 5,000 kilograms. V initial is 4 meters per second. Make sure you square that. All right, so what do we have here? 8 squared is 64 times 2,500. 2,500 times 64 is 160,000. All right, 160,000 joules minus. We know from the previous problem this was 40,000 joules. And so we're getting a change of 120,000 joules. All right, the change in kinetic energy from a speed of 4 meters per second to a speed of 8 meters per second is 120,000 joules. All right, right here, when the truck was traveling at 4 meters per second, it had 40,000 joules. When it increased its speed to 8 meters per second, now it has 160,000 joules. So that is a change of 120,000 joules. All right, you should put that number down there. I'm out of space. I'm going to put it over here. All right, the change in kinetic energy for the second part of this problem is 120,000 joules. All right, now, I said a moment ago, you could factor out the 1/2 m. Let's do it that way now. All right, it's a little bit easier. The math is a little bit easier if you do that. All right, it's the more elegant way to do this mathematically. So let's do that. All right, so, and you'll see you're going to get the same answer. All right, so 1/2 m V final squared minus 1/2 m V initial squared. All right, you're going to factor out the 1/2 m. So 1/2 m gets factored out, and it's going to be V final squared minus V initial squared. We could have done this the first time also. All right, so what do we have here? Let's start plugging in. 1/2 m is 5,000. 5,000 kilograms. All right. Now, my V final is 8 meters per second squared minus 4 meters per second. All right, you know what? We need more parentheses there. That's getting parentheses there. Be careful. All right, all those, you need all those parentheses. All right, now. All right. 64, 8 squared minus 4 squared. 64 minus 16. All right. 64 minus 16, and half of 5,000 is 2,400. All right, so you've got 48 over here, so you've got 2,500 times 48. all right, 2,500 times 48. And you see you get 120,000 just the same. All right, so again, you're going to get the same answer. You're just doing the math a little bit more elegantly. Factor out the 1/2 m, all right, and the change in kinetic energy when the truck goes from a speed of 4 meters per second to a speed of 8 meters per second is still 120,000 joules. All right, so this was just an example of calculating a change in energy. How much energy did it have at the end minus how much energy did it have at the beginning? How much was the change? All right, now I'd like to talk about a different reason why you might want to know the effect of a change in mass or speed on an object's kinetic energy. All right, so let's actually go with the truck again. All right. Now we know that the kinetic energy of an object is 1/2 the mass times its velocity squared. Now, if, for example, we were to double the mass of the truck, if the mass of the truck was 10,000 kilograms instead of 5,000 kilograms, all right, so what you would do is, since the mass doubled, you would simply put a 2 here, right, to show that is what doubled. All right, I guess we're going to do it in blue because the red isn't writing very well. So if the mass doubles, all right, then the only thing that happened, all right, is that the 5,000 kilograms changed to 10,000 kilograms. The mass doubled. All right, and that means that the kinetic energy would double. This is a direct relationship. The relationship between mass and kinetic energy, according to this equation, is direct. So if the kinetic energy was, all right, remember the kinetic energy was 40,000 joules. If you double the mass of the truck, or you look at another truck traveling at the same speed, all right, which was 4 meters per second at the beginning, all right, then if you look at a truck that is double the mass, 10,000 kilograms, then that truck's kinetic energy is going to be 80,000 joules. All right, double, direct relationship. If the mass doubles, the kinetic energy doubles. Now, what about doubling the velocity? How is doubling the velocity different? Well, the velocity is being squared. The velocity is being squared. So let's see how that would be different. Let me go back to the original equation. All right, let me go back to that. Fix that. All right, so the original equation, 1/2 mv squared. So if the velocity doubles, all right, this is not just a direct relationship. This is an exponential relationship between velocity and kinetic energy. So if you double the velocity, there's a squared there. 2 squared is 4. That means that since for the 5,000 kilogram truck, since the kinetic energy, right, when the truck was traveling at 4 meters per second, the kinetic energy was 40,000 joules. When we doubled the speed of the truck to 8 meters per second, when we doubled the speed of the truck, square that doubling, the kinetic energy of the truck is now 4 times the original kinetic energy. So it's going to be 160,000 joules. And we calculated that already. We know that's correct. All right, so very, very simply, all right, the relationship between, according to this equation, The relationship between mass and kinetic energy is direct. If you double the mass, the kinetic energy doubles. The relationship between velocity and kinetic energy is exponential. In this case, it's squared. So if you double the velocity, the kinetic energy is going to quadruple. It's going to be 4 times what it was originally. All right, so this is a shortcut way to figuring out how the kinetic energy of an object changes when either the mass changes or the velocity changes. The gravitational potential energy possessed by an object depends upon the object's mass, that would be the kilograms, the planet that the object is near, the planet, the satellite, the asteroid, whatever celestial body the object is near, that would be the acceleration due to gravity, or meters per second squared, of that planet or celestial body, and the height of the object. That would be in meters. Now, that means that the equation for, look, gravitational potential energy. Gravitational potential energy can be abbreviated or symbolized, little g, all right, PE, gravitational potential energy. And what is it based upon? The object's mass, the acceleration due to gravity of the planet that the object is near. All right, usually that's going to be Earth, where this number will be either 9.81 or rounded up to 10. And the height of the object above the surface of that planet. Let's do some problems. Let's calculate the gravitational potential energy of a 30 kilogram child standing on the ground. So, the equation for gravitational potential energy, PEG equals m times g times h. Now, the mass of this child is 30 kilograms. If no other planet or celestial body is mentioned, we assume that the person or the object is on Earth. So the acceleration due to gravity, we're going to put 10 meters per second squared. All right, now, if the person or the object is on the ground, then the height is 0. All right, so what we see here is that when an object is on the ground, where the height is 0, the gravitational potential energy is also 0. All right, we really didn't have to do anything here because we knew that the height was 0, and 0 times anything else is still going to be 0. So for this first problem, the child has 0 gravitational potential energy because they are standing on the ground where the height is 0. Now, let's calculate the gravitational potential energy of the same child 2 meters up on a ladder. So, the gravitational potential energy equals m times g times h. All right, the mass is 30 kilograms. G for the Earth is 10 meters per second squared, and the height is 2 meters. So the gravitational potential energy possessed by the same child 2 meters up is 30 times 10, that's 300, times 2 is 600 joules. So again, gravitational potential energy depends upon the mass of the object, the acceleration due to gravity of the planet that the object is on or near, and the height above the ground for that object. Now, what would the same child's gravitational potential energy be 3 times higher? instead of 2 meters, now the child has climbed 6 meters up the ladder. That's really high. That's kind of like climbing up a fire truck ladder. That's 18 feet, or a little bit more. Wow, that's pretty high. All right, anyway, what is the child's gravitational potential energy 6 meters up? Instead of 2 meters up, the child is now 6 meters up, 3 times higher. So, the gravitational potential energy equals the child's mass times the acceleration due to gravity of the Earth times the height, which is 6 meters. So 30 times 10 is 300, times 6 is 1800. In terms of significant figures, we've got 1, 2, 3 significant figures. So we really don't want to put a decimal there. That would be 4 significant figures. An old way to show this would be to put the line right above there, or put it into scientific notation where these 3 figures are significant, all right, times 10 to the third. All right, so either one of these shows the correct number of significant figures given three significant figures, just a mention of significant figures. All right, now, you noticed from the previous problem that when the child was 2 meters up in the air, the gravitational potential energy of the child was 600 joules. Now, when the child is 6 meters up, right, which is times 3, right, 3 times the height, the gravitational potential energy is 1800 joules, or again, 3 times the gravitational potential energy. So what you have here is a very simple, straightforward, direct relationship between height and gravitational potential energy. If the height changes to 3 times what it was before, the potential energy is now 3 times what it was before. When the child was at a height of 2 meters, the potential energy was 600 joules. When we change the height to 6 meters, or 3 times the height, we now have 3 times the amount of gravitational potential energy. 600 times 3 is 1800. Here we have another very, very simple problem, but I just want to make sure that you understand the wording and how simple it is to figure out what they're looking for. Here in problem number 4, we're being asked to calculate the change in gravitational potential energy from the ground to the 2 meter height, and from the 2 meter height to the 6 meter height. Okay, we're asked to calculate the change. All right, so from 0 meters to 2 meters, the change is final minus initial, always. So the final, PEG, would be mgh final. Now, the mass of the child does not change, and the acceleration due to gravity of the Earth does not change. All right, minus, now here, mgh initial. Now, the initial height is 0, so this goes away. This whole part here drops out. The initial height is 0, and 0 times mg is all 0. So you find that the change in height here, all right, is just the mass of the child, 30 kilograms, times the 10 meters per second squared for the Earth, times the final height, which is 2 meters. All right, so the change here, okay, the change from a height of 0 to a height of 2 meters is 30 times 10 times 2. Right? That's that same 600 joules that we calculated earlier. Right? So that's how much her gravitational potential energy changed when she went from the ground to 2 meters up on the ladder. Right? Now, here, what was her change in gravitational potential energy? Look at the PEG for gravitational potential energy. All right, so her potential energy final, mgh final minus mgh initial. All right, now I'm going to move over just a little bit so I have enough room. Maybe I better move over some more. All right, her mass. Now, I tell you what, we could factor out the mg. Let's do that. All right, factor out the mg, right? Factor out this mg and this, pull them out, and then you've got h final minus h initial. All right, that'll save us a little bit of math, a little bit of writing. All right, so m, 30 kilograms, g, 10 meters per second squared. All right, h final, the height final is 6 meters. Be very careful not to confuse the final or the initial. Be very careful. The final height is 6 meters. The initial height, 2 meters. She started here, went up to there. This is initial. All right, this is final. It's a very good idea to think about what you're writing down, label things clearly so you don't make little mistakes. All right, I mean, physics can be hard. You don't want to make mistakes on the easy stuff. The easy stuff you got to nail. All right, there'll be plenty of hard stuff to make mistakes on. All right, here we go. Final height 6 meters, initial height 2 meters. So what we've got is 30 times 10, which is 300. 6 minus 2 is 4. 300 times 4 means that the change, I think I can just squeeze it down here, the change in potential energy is 300 times 4, or 1,200 joules. Right? The change is 1,200 joules. Now, if you remember, what we calculated previously was that at 2 meters, let me write this, all right, when we were at 2 meters, her potential energy was 600 joules. When we went up to 6 meter height, her potential energy was 1,800 joules. What's the change? The difference between those two? All right, just as we calculated, the difference between those two is 1,200 joules. All right, so just a little bit of, okay, what exactly are they asking us to calculate? All right, so if they're asking us to calculate a change, it's going to be a final minus an initial. The last type of energy we need to look at is called elastic potential energy. Sometimes it's called spring potential energy, which is why the abbreviation you will often see is PES, for spring potential energy. Now, what is elastic or spring potential energy? It's the energy stored in an elastic object when it is stretched or compressed. All right, so for example, there are 2 types of springs. There's the type of spring that you stretch. So what you would do is stretch the spring, which stores energy, and then when you let go, the spring springs back. Again, if the spring is small and you stretch it, you've now stored energy in that spring, and when you let go, it springs back. Now, a compression spring works in the opposite way. A compression spring is a little bit longer, and when you press it, you're storing energy. When you let go, it springs back to its original length. Now, cars and trucks have giant springs that act as shock absorbers. So when a car or a truck goes over rough terrain, right, or a rough road, the springs kind of reduce the impact of the bumps on the chassis of the car. That's a good thing. All right, now, a rubber band. A rubber band is a type of device that you stretch, right? It's this type. You stretch it, right, and then when you let go, it springs back together again. Again, these are all elastic elastic objects, when you stretch them or compress them, they go back to their original length. A trampoline or a diving board is an elastic object. So how is elastic potential energy stored in an elastic object calculated? Well, first of all, the symbol would be PES, and that stands for spring potential energy. And it's going to be equal to 1/2 K. Now, K is called the spring constant, right? And every object has, every elastic object has a constant, right, calculated specifically for that object, times x squared, where x is the length of the stretch or the compression. How much was the object stretched, or how much was the object compressed? All right, stretched or expanded or compressed. All right, so now what exactly is a spring constant? Using the examples of springs, for example, in a pen, the click-click type of pen, there's a tiny itty-bitty little spring inside the pen. The spring might be about that big, and it's made out of very thin wire. So the spring constant for a small, weak spring, like the spring that you find inside of a ballpoint pen, might be 3 newtons per meter. Right? It's going to be a small number because that is a small, weak spring. It doesn't take much force. How many newtons? Only 3 newtons. All right? And these numbers are made up for relative discussion. All right? But a small number. Maybe it only takes 3 newtons, all right, to compress a tiny little spring like you find inside of a pen. All right? Now, in trucks, cars, airplanes, you have these heavy, giant springs. It might, on a truck, that spring might be this high, and the cable used to make that spring might be this thick around. All right? It might take 300, all right, to compress that spring, all right, that acts as a shock absorber on a car, all right? It might take 300 newtons or 3,000 newtons or maybe even 30,000 newtons for an airplane, all right? So the spring constant for a large, heavy spring that's very hard to compress or hard to stretch is going to be a big number, all right? So what the spring constant does is it tells you whether the spring is a small, weak spring or a large, heavy spring. Little, weak spring, low number. Big, heavy spring, big number. And the unit is newtons per meter. All right, now here, the length is going to be meters, and that's going to be meters squared. All right? So that's your equation for calculating elastic potential energy. The type of pen that you click and the pen part comes out the bottom, and then you click again and it retracts back up into the pen, has a tiny spring on the inside. Now, since this is a tiny, weak spring, its spring constant is going to be small, maybe 3 newtons per meter. So, calculate the elastic potential energy stored in this spring when it is compressed 2.00 centimeters. Now, because the spring constant is in newtons per meter, and the meter is part of the Newton, right? There's a meter inside the Newton unit, and there's also a meter here. You can't use centimeters in this calculation. You're going to have to convert those centimeters to meters right away. So let's do that first. All right, so factor label method, 2 centimeters. All right, I want to convert centimeters. I want to get rid of the centimeters, convert them to meters, right? And 1 meter equals 100 centimeters. So it's going to be 2 divided by 100. So you're going to be moving that decimal place, all right, 2 places to the left. All right, 2.00. We're going to move it 2 jumps to the left. So this is going to be 2 centimeters is going to be 0.0200 meters. All right, so we're going to be using that number, all right, in our calculation, 0.0200 meters. All right, now, the equation for elastic potential energy, all right, PES equals 1/2 kx squared. Let me see if I have a marker that's working a little better. How about this one? All right, so 1/2. Now, K, the spring constant, is 3.00 newtons per meter. 3.00 newtons per meter. All right, X, the amount that the little spring is compressed, in this case, 0.02 meters. 00 meters. So how much energy is stored in that spring, that tiny little spring inside the pen? All right, oop, oop, up, whoa. Okay, don't forget to square. All right, here we go. All right, 0.02 squared, all right, is 0.0004 times 3, all right, and then times, divided by 2. All right, so it's 0.0006. All right, this is a type of energy, so it's going to be joules. All right, so really what you've got here, 1, 2, 3, 4 jumps, so it's 6.00 times 10 to the -4 joules of energy stored in the teeny little spring inside of a pen. All right, let me just double check this math. 0.02 times 0.02, yep. Oh, wait a minute, 0.02, oops, 0.02 times 0.02, yes, okay, times 3 equals divided by, oops, okay, 0.0006, okay. Now, let's take a look at how newtons per meter times meters squared translates to joules. All right? So, all right, you've got newton per meter, right, times meter squared. All right, so what's really happening here is that this meter is canceling with that meter. So what you're really getting here is Newton meter. And if you saw some of the earlier videos on work, energy, and power, a Newton meter is the same as a joule. A Newton meter is the same as a joule. So that's where we got the joule from. All right? Moving on to one more problem on calculating elastic potential energy, but this time in a big spring. So in the last problem, we looked at a tiny little spring inside of a pen. In this problem, we're talking about a giant, heavy spring. It might be this tall. That's inside of a car or a truck. You would need a spring for each of the wheels to kind of act as shock absorbers. And then there's also shock absorbers. That's a whole nother part. But in any case, cars and trucks, airplanes, etc. do have giant springs. Many cars and trucks have a big heavy spring on top of each wheel to act as a shock absorber. Since this is a big heavy spring, the spring constant it's a big number, 300 newtons per meter. Right now, cars and trucks, it might be 3,000 or 30,000 newtons per meter. But let's just start with a number like this, okay? Much bigger than the 3 newtons per meter that we used in the previous problem. Calculate the potential energy, the spring potential energy, or elastic potential energy stored when this big, heavy spring is compressed 2 centimeters, about that much. Now again, you immediately have to convert the centimeters to meters because spring constant has newtons, spring constant has meters, right? Centimeters have to be converted to meters. All right, so we do that first. And now we calculate the elastic potential energy, right, or spring potential energy. All right, spring or elastic potential energy stored in this spring when we compress it 2 centimeters. 1/2 K. K is the spring constant. In this case, 300 newtons per meter. The amount of compression is 0.02 meters. Make sure that gets squared. Yeah, guys, don't forget to square. Don't forget to divide by 2. All right, watch out for the 2's. All right, lots of mistakes to be made with the number 2 in a lot of the different physics equations. All right, so 0.02 squared, all right, times half of 300 is 150. So 0.02 squared and then multiply by 150, you're going to get 0.06 joules. You've got 3 significant figures, so here we have 1, 2, 3 significant figures. All right, so that was an example of how to calculate elastic potential energy. It doesn't have to be a spring. A rubber band can have a spring constant, a trampoline has a spring constant, a diving board has a spring constant, right? Anything that stretches or compresses and then goes back to where it was originally has a spring constant that can be calculated. Right, so just a little wrap up here about what this video was about. Recognizing different types of energy in physics problems. Okay, so when you're reading a physics problem, you're looking for clues as to, well, what are they asking me to calculate, or what are they asking me to figure out? Now, for kinetic energy and gravitational potential energy, you're probably going to see a mass. Right? For elastic potential energy, you're probably going to see K, a spring constant. Now, normally, the mass, or the spring constant, or the acceleration due to gravity of the planet, for that matter, are not something that's going to change very much. Right? So normally, the mass is not the issue. The acceleration due to gravity is not the issue. The spring constant is usually not the issue. Right, so what you want to look for clues, if the problem is about calculating kinetic energy, they're probably going to mention a speed, a velocity. All right, if they give you a velocity, they probably want you to calculate kinetic energy. Right, you're going to need a mass and a velocity to calculate the kinetic energy. If they mention a height, right, and height could be h for height or displacement, a vertical displacement for height. If they mention a height, they probably want you to calculate gravitational potential energy. Keep in mind you're going to need the mass of the object, right? And you're going to have to know what planet you're on, so you know the correct acceleration due to gravity. Right? And finally, if they mention a change in spring length, and for that matter, if the problem doesn't mention a spring, in your first year of physics, most of your elastic potential energy problems are going to be about springs. You know, later on, as you take more physics, they might mention a trampoline or a diving board or something else that has some elasticity to it, a rubber band, right? But at least in the first year of physics, if the problem mentions a spring, they're probably asking you to calculate the elastic potential energy. You're going to need the spring constant, and you're going to need to know how much the distance was that the spring was either stretched or compressed. Right? So again, If you see mass and velocity or speed in the problem, you're probably being asked to calculate kinetic energy. If you see mass, the name of a planet or the acceleration due to gravity of a planet, and a height, you're probably being asked to calculate gravitational potential energy. If the problem mentions a spring and gives you a spring constant, right, and a change in length of that spring, either stretching the spring or compressing the spring, you're probably being asked to calculate elastic potential energy. Now keep in mind, if you're given the kinetic energy, you can calculate either the mass or the velocity. If you're given the gravitational potential energy, you can calculate one of these. Right? And if you're given the elastic potential energy, you could be asked to calculate, for example, the spring constant. All right? But just in a general way, speed or velocity, they're talking about kinetic energy. Height, they're talking about gravitational potential energy. Change in the length of a spring, they're talking about elastic potential energy. Make it really, really simple, right? And again, keep in mind, the unit for all types of energy and work is the joule.